Hello, we're going to start up in just a second. Okay, it looks like it's working, which is good. Welcome to the 8th live lecture and the probably the 4th virtual office hours for the POSA Concurrency MOOC. Today we're going to talk about a couple things. First thing, just to change it up a little bit, I'm going to go over my solution to programming assignment number 2, and of course take any questions that you may have. We'll actually look at a couple of different solutions that I came up with. And then we're going to go and finish up a couple more of the patterns. We'll finish up the active object pattern, discussion about implementation and application in Android, and we'll also talk about the half sync, half async pattern. And that will basically finish up the lecture portion of the course. We will have another virtual office hour session next week, probably on Thursday again, so that we can go over the solution to programming assignment number 3. But aside from that, we're going to be done with the lectures. So that'll give people a chance to catch up with any lectures that they haven't had a chance to do yet. So without any further ado, let's go ahead and start. Go ahead and share my screen. So what I'm going to do now is I'm going to go over a couple of different solutions to programming assignment number 2. If you recall, this programming assignment is the one where we had to write a ping pong program that would go back and forth and print out text, as well as be able to display flashes to the screen every half a second or so. Let's go ahead and start with the output strategy, which is very simple. The purpose of the output strategy is to decouple the play ping pong class from the way in which output is actually displayed. And so you could change that without having to change the rest of the implementation. That's why it's a strategy. And you can see here that we go ahead and keep a weak reference because we have to be able to access the activity that we're talking to. And here's really all you need to do. You need to use the weak reference in order to get the main activity. And then if that has not disappeared for some reason, then you simply go ahead and print the output string to the print method of the main activity, and we put a new line at the end just so it'll be new line terminated. That's, of course, depends on how you do your other implementation, but that was the basic idea. And if for some reason the activity goes away, then we catch an exception and print out a message to our error log. And of course, there are various ways in which the activity could go away, so we have to be prepared to handle it in a sensible and graceful manner. We'll come back later and talk about the print statement, and then we'll explain how the actual activity itself works later. Okay, so let's go ahead now over here to play ping pong. And as you can see, play ping pong is a class that implements runnable. And we have it implement runnable so we can start it to run in a separate thread. And when we talk more about the main driver program, I'll explain why it's the case that we need to be able to do this, why we need to be able to have it correctly run in a thread. Let's take a look at some of the various parts of this. So here is the ping pong class implementation. As you can see, it's got an enum in it called ping pong, and ping pong has ping and pong enumerals or enumeration literals, or whatever you want to call these things, enumeration fields, enum fields, etc. And so we'll see how that gets used later. I use it in a couple of rather clever ways, I think. We also have something that keeps track of the number of iterations used to run the ping pong algorithm. This, of course, is going to be passed in to the into the constructor of play ping pong. Here's where I ended up putting the array of ping pong threads. We'll see what a ping pong thread is in a minute. Those are essentially subclasses of the handler thread class in Android, and they're what are actually going to be running concurrently. And you'll notice here that I have two of them. One of them is going to be the ping thread, and the other of them will be the pong thread. So we got ping and pong threads. We'll see how that works in a second. We keep track of our output strategy just so that we have a way to be able to decouple the output from the way in which we handle it in the main driver program and from the play ping pong class itself. And then down here is where we start filling in the blanks that are more interesting. So the first thing we do is we define ourselves an array of ping pong handlers. And you can see what I do here is I make an array that is as large as the size of the ping pong values. So the ping pong enum values.length will be 2, of course, because there's a ping and a pong. And so I make a new handler array that has 2 items in it. And then down here, I go ahead and I make another cyclic barrier that also has 2 elements in it, one for ping and one for pong. And that's also what gets initialized. Notice that both of these things are defined as final, which means we don't have to worry about them with respect to them being accessible when the threads start to run. Final is a happens before barrier, and so this will be initialized properly by the time the program threads start to access it. Go down here, make this a little bit smaller so we can move around a little easier. There we go. Oops, how about that? There, I think that's right. So now we have class ping pong thread. Class ping pong thread extends handler thread. Handler thread, of course, is the special class in Android that has the properties we talked about way back in the looper lecture, where we talked about how handler thread could be used, and in order to be able to have a thread run in the background. It also implements handler callback. So we have handler thread, which is a subclass, or ping pong thread is a subclass of the handler thread superclass, which in turn is a subclass of thread. And then we have a handler callback. And if you go back and watch the videos, I think it's from week 2, where we talked about the sending and handling messages, you see that there's a couple different ways to handle messages. One way is to extend from the handler class, and the other way is to implement the handler callback mechanism. Well, since we're already extending handler thread, we went ahead and implemented the handler callback, and you'll see how that gets used later. That way we don't have to inherit from handler directly. Ping pong thread keeps track of the type of ping pong enum it is, whether it's a ping or a pong. It also keeps track of the number of iterations completed thus far. You'll see how that's used later. We keep that as a separate instance variable so that we don't have to worry about synchronization or locking to access it, because there's a unique copy for each of these objects. Here is the constructor, ping pong thread constructor. As you see, it takes the type of ping pong thread, and it goes and uses the toString method of the ping pong enum to initialize the handler thread, which wants a string name, which will either be ping or pong. We use that later. And then we go ahead and we initialize the type, the ping pong type, and we store it in a local variable, which is called myType. So that keeps track of that. You'll see how we use that in a second. So far, it's pretty straightforward. Now things get more interesting. Here's the onLooperPrepared method. Remember, onLooperPrepared is a hook method that gets called back by the I guess it's actually the run method that's part of handler thread. So handler thread uses the template method pattern. It defines a run method, which is called when the handler thread is started, and that run method turns around and prepares the looper, calls onLooperPrepared, which is this hook method, and then it calls basically looper.loop. And so this is the onLooperPrepared method. This method is called back in the context of the handler thread. It's not called back in the UI thread or the main thread. It's called back in the context of the handler thread. And that's very important here because we're going to end up creating a new handler here. As you can see here, we say we're going to create a new handler with this. And we need this because this is actually the instance of play ping pong thread. And that, of course, is going to ultimately end up allowing us to use the handler callback. So now we're connecting with the handler callback, which is us. And that means that when the handler receives a message, its handle message method will automatically be called back. So that allows that to happen. If you go take a look at the handler class, you'll see that one of the methods that it provides for its constructor is the ability to pass in a handler callback, which turns out to be this in this context because we implement the handler callback interface. Now we also do some clever stuff here. We take our MyType enum, which is either ping or pong, and we grab the ordinal value of that. So if it's ping, it's 0. If it's pong, it's 1. And then we go ahead and we index in either 0 or 1 into M ping pong handlers, and we store our handler in that location. And of course, by doing this, we ensure that the ping thread and the pong thread will initialize different portions of the M ping pong handlers array. One at location 0, one at location 1. So again, we don't need any locking to do this because they're indexing into different locations in the array. Now, that's all well and good, but the problem here is we don't know whether the ping thread starts first, followed by the pong thread, or the pong thread starts first, followed by the ping thread. So to make sure that this all works properly from the point of view of starting up, we use a cyclic barrier, which is essentially a barrier that's used to wait for all threads to reach a certain point. And so we initialize this with a count of 2. So you go back up here, you can see we initialize this with a count of 2. And then the way this works is that only after both threads have called await on the initialization barrier do they both proceed through here. So if the ping thread gets there first, followed by the pong thread, or the pong thread gets there first, taken by the ping thread, it doesn't really matter. It'll work in the right order and the right way, and they both get released once they're both initialized. Now, here's what I do next, and this is basically just to get things started. So what I do is, in my particular case, I check to see if I'm the pong thread. You can also do the same thing with the ping thread. It doesn't really matter. Same difference. I just use the pong thread. And if I am the pong thread, I go ahead and I get the ping handler, which is obtained by using ping's ordinal value. And then I go and get my value, because I'm the pong thread, of course. And I could have said ping pong.pong.ordinal, wouldn't have mattered. So I get handlers for the ping thread and the pong thread. And then I go and I say, hey, ping thread, please give me a message that's associated with you as the target. So this is the ping thread will be the target. And please make the pong handler the object. And then I say, and that's what I call a request message. And then I go ahead and I say, I would like to request that this message send itself to its target. And what that does, of course, is that ends up calling the handle message method on the ping thread. And that's where things are all going to start up and begin to run. Now, there's other ways to do this. This is not the only way to do it. This is the way I did it for my first implementation. I'll show you a second implementation shortly that does it a slightly different way, that is arguably a little cleaner. But this was a nice way to just kind of get everything up and running. And again, there are other ways to do this. This is the way I thought was the cleanest way to do it. So once the pong thread sends a message to the ping thread, from that point onward, everything is done through the handle message method. So here's handle message. Handle message takes a message, which is a request message. And again, there's lots of different ways to do this. Here's the way I did it. This one comes in here and it checks to see whether or not we have completed the maximum number of iterations or not. And as you can see here, the max number of iterations is something that'll be set in the constructor. And this is then going to, actually, I think it's the constructor of play ping pong. And If we haven't completed all the iterations, we print out the name of the handler task, because that is where we encoded ping or pong. And then we also print out the iteration that was just completed by first pre-incrementing it. So it starts at 0 and it goes to 1. So that'll print out, say, ping 1. And so if we're not done with our iterations, that's what we do. If we have completed all the iterations, then we tell ourselves to go ahead and shut down. And I guess I had a little print statement in here just for debugging purposes, but I'll remove that. So we then go ahead and tell our looper to quit. Now, there's a lot of different ways to quit. There's quit, which just says, I'm done. There's also quit safely, which lets all the other things finish before we're done. In this case, we're done, so we just quit. So this goes ahead and says to our looper, please shut yourself down, which means that this guy won't run anymore. In either case, whether we printed something or whether we quit, we then go ahead and grab the reply handler out of the OBJ field in the request message. So this is the guy, this is the handler that we're going to be using to send a response to. So for the ping thread, we'll send the pong thread the ball back. If for the pong thread, we'll send the ping thread the ball back, and so on. The next thing we do is just a little sanity check. We check to see if the other handler thread is even alive or not. If it's not alive, then it's shut down, and so we go ahead and quit. If it is alive, it might shut down, depending on what happens, but that's not our worry at this point. So we just check to see whether it's quit, whether it's shut down, in which case we also quit. Then all we do here is we simply go ahead with the reply handler. So this is the guy who we're going to be replying to. We make a new message where we use the reply handler to make itself the target of the message. And then we go ahead and we stick ourselves as the reply to that guy. So the reply handler for the reply message is used to be the target for the new message. And then we make ourselves the reply to that message so that the other guy can get back to us. And then we go ahead and we send that message to the reply message. And you'll notice that this code works correctly whether or not this is the ping thread or whether or not this is the pong thread. It works perfectly well in both cases. So that's basically handle message call. Pretty cool stuff, pretty clean, very symmetrical. And we have to return true just because of the way that the handle message method works. I added this particular method. You do not need this method for your solution. I just added it later because it seemed like a good idea. This is a method that can be used to shut down the various threads that are running. And I'll show you how it's used in the main program. This, again, is an optional thing. You do not need to have this. It's not part of the assignment. There's no to-do tags here at all. All this does is it simply iterates through the ping and pong threads, and it tells them to quit, to shut themselves down, and then it interrupts the thread in order to be able to stop it if it was in a long-running operation. In this particular case, we don't really have the interrupt, but it's not a bad idea to get in the habit of using it just because that's a good thing to do. And I think you typically want to quit first and then interrupt as opposed to the other way around. All right, but that's totally optional. You don't need that. Here's the constructor for play ping pong. It takes the number of iterations and the output strategy, and it caches them or stores them in fields. That's pretty straightforward. And then here's the main run method. So the first thing we do is we iterate through the ping pong threads. We have 2 of them, keep in mind, and we start both of them, so they both start, and that causes their run method to get called in the handler thread, which causes the on looper prepared hook method to get called back, which sets everything in motion. And then we go ahead and we wait for those threads to stop. So this is a little barrier synchronization, which doesn't need to be a cyclic barrier, although it could be. So here we go ahead and start off the 2 threads, and then we go ahead and loop through the threads, and we join with both of them. And when both the threads have been shut down, and you can see how they get shut down if you look up here, it's when their loopers quit, either when they're done with the iteration or because the other looper's gone away. In either of those cases, those threads stop, join will return, and after both those threads are done, we go ahead and we print the done field. And so we're basically finished. And that's it. That is basically the implementation of my solution. So what I'm going to do now is I'm going to take some questions, and then I'm going to show you an alternative solution, and then I'll also show you the main program, just because that's kind of interesting as well. All right, so let's see what let's see if people have any questions. Is it necessary to have the arrays for the handlers? If people define two handlers and everything works fine, that's fine. No need to have two arrays if you don't like arrays. I'd like the array solution because, as you can see, it's very, very easy to use enum methods like ordinal to use the values of the ping and pong enumerals or enumeration literals as indices into the array. So I found that I was able to write code that required few, if any, special cases, but you don't have to do it that way. That's perfectly fine. In the ping pong constructor, don't we need to initialize m iterations completed to 0? Java does that for you automatically, so you don't need to do that yourself. Let's see, people saying, has the class started yet? Yes, it has started, as you can probably tell at this point. And let's see, there's another question. So yeah, so sometimes people didn't properly join the threads, and so as a result, or they didn't properly exit the threads, and so as a result, the done method will not be printed. That's really incorrect. The program needs to print done, because what that most likely means is that one of the threads is hung and is not returned, and that's of course a bad thing. You don't want threads to be stuck in infinite waits, because that's not a good way to write code. So that's a good question, and it's actually not really correct result. You should have the done printed out at the end. So people are giving suggestions on other ways of being able to check if the other thread is alive. Yeah, there's all kinds of ways to do this. I'm showing you one way. You can do it other ways. Don't worry about that. Let's see. Is it wrong to do other handler dispatch message? You should not be calling dispatch message. Dispatch message is not intended to be a method that you call directly. You should be using either send message, or you should be using the send to target method, but don't be using dispatch method. That's not correct. Okay, I think that's most of the questions we have so far. That's okay. I will go ahead and show you my next solution, and then if there's other questions, you can go ahead and post them as well. So let's go ahead and share the screen again. Here's the next solution. This solution is a little bit cleaner in certain ways because it doesn't require such a clever approach in a special case in the on loop or prepared method. So it's arguably a little bit cleaner. So let's take a look at this. So the first part's the same. We have the M ping pong threads, which is an array with a ping pong thread with ping and a ping pong thread with pong. The handler array is also the same. It's got a value of 2. In the new solution we're looking at here, however, I make a cyclic barrier with a count of 3. So it's the length of the ping pong values, which is 2 plus 1. And you'll see how I use this a little bit later. It's a little bit, arguably a little bit cleaner, maybe. Keep in mind that I'm just showing you another solution. This is not one you have to follow, just to show you there's other ways to do it. Here's the new on loop or prepared method. As you can see, all this does is it just initializes the ping and pong indices of the M ping pong handlers array. So that's all it does. It doesn't do anything else. So that's just what's going to get called. Here's the handle message method. I further refactored this a little bit, so it's a little bit cleaner. I now have a method that's called get reply handler, and it does a little bit of the checking. And once we get the reply handler, then we go ahead and we return the ball to the reply handler. And you'll see in a second how that's going to work. Here's get reply handler. All get reply handler does is just kind of refactor the code so it shields you from some of the low-level details of checking if the other thread's alive. As somebody pointed out, you don't have to do that if you do it other ways. That's just another way to do it. Here's return the ball. So you can see return the ball is very clean. It uses another factory method called make message that takes a target handler and a reply handler, and it makes a reply message. So we'll look at make message in just a second. So this is just even more factored out code. Here's the make message method. All it does is it just uses the target handler to get a message that's got the reply handler as the OBJ field. Here's the start hitting the ball method. We'll see how start hitting the ball is used in a second. This is used to start hitting the ball from the ping thread to the pong thread. It's going to wait in the initialization barrier, which has now been given a count of 3. So this is the third thread that'll call it. So once the handler threads are initialized, this guy can then proceed also. And he just goes ahead and creates a request message that has the ping and the pong handlers set properly, and then sends that message to the ping thread to start things off. Shutdown thread is the same. The constructor is the same. Here's the run method. You can see what it does is it comes in, creates both of the threads, starts hitting the ball. So it hits the ball to the ping thread first, and then it goes ahead and it waits for everything. It just goes ahead and joins on the release of the other threads. And everything else from that point onwards is driven by handle message calls, which just return the ball. So the ping thread starts hitting the ball, and then whoever gets it next returns the ball. And here's just return the ball. So arguably, this is a little bit cleaner because it's a little bit more clear what's going on, and we're not being quite so clever in the on looper prepared hook method. But as you can see, it's just another way to do it. I'm absolutely sure there will be other people in the class who have other solutions a little different from mine, but that's okay. So shouldn't be a problem. All right, let's go ahead and go back and take some questions. What does 0 mean in send to target method? I'm not quite sure what you mean by that. There is no 0 in the send to target method. There's a 0 in the call to obtain message, and that's simply used as you need to provide that field as the value of the what parameter in the message, and there was no what parameter of any interest or meaning. So I just went ahead and passed the 0 there, but that was hidden inside the factory method, so it was a little cleaner. Are there multiple ways of calling a method in an activity class from a non-activity Java class? I'm not really sure what that means, but I'm assuming what you might be referring to is how do you have callbacks from one class to another class that's an activity class. And so if you take a look, for example, we'll go take a look at this just for kicks. Let's go ahead and bring up the code again real quickly, and I'll show you. All right, so I think what this question is asking is this. So here's an example where I have a class called output strategy that needs to access an activity. And so to avoid various issues about memory leaks, as described here in this link, we use a weak reference. And this is how we go ahead and access the outer activity from the class that is using the activity to call it. So that's a common way of doing it. It's not the only way of doing it, but it's one of the more common ways of doing it. And of course, there's all kinds of other ways you could use to have classes communicate back and forth. You can have them basically do things like pass messengers to each other or pass messages to each other. That's another way of doing stuff. So a lot of different ways of doing things. Okay. So there's a question here about dispatch message. So please go back and watch the videos from week 2 on the implementation of the Hammer framework. There's a whole discussion in there about dispatch message versus send message, and I'm not going to repeat the whole discussion, but in a nutshell, do not call dispatch message yourself. It's really meant to be an internal call. just call send message and everything will work out just fine. Android recommends against enums as memory intensive. Why did you choose it? Well, first of all, where does it say that? Go ahead and send a link if you have a link to it. But in this case, it's insignificant to the extreme to use an enum, and I liked it because it allowed me to be able to package up a whole bunch of things. I could get the string value from the enum, I could get the ordinal value from the enum, I could get the length of the enum, all in one clean way. And if I hadn't used an enum, I would have had to have gone ahead and defined a bunch of other fields like strings and constants and so on. So I suspect very quickly that any, quote, memory savings from not using enum would have quickly been subsumed by having to define all those other things, number one. And number two, it was just way cleaner to use an enum. So given all the things that people use to allocate memory that are memory hogs, the use of an enum is probably very low in the list of things to worry about. Somebody keeps getting a malformed URL exception. So, well, you're going to have to take a look and see why you're getting a malformed URL exception. What kind of URL are you passing? I'm guessing that you're probably passing a malformed URL. So take a look. You might take a look at the default URL that we use, the one that points to robot.pmg, and see what the format is for that, and then try a couple other URLs that you know are correct. Try using them through a web browser, for example, to make sure that they work properly, and then see why they're failing. You might also, crank open the debugger or put some log statements in and so on. That's my guess. By the way, there's also on the website for the course now a little video showing my solution for assignment number 3. And it's really simple. It's basically the same user interface as assignment number 1, except rather than downloading the original image and displaying it, it downloads an image and it goes ahead and applies a grayscale filter to it so the color disappears. In assignment 2, will it be evaluated with error management? So go back and take a look at the rubrics for assignment number 2, and you'll see what they ask for. So they say, does the program run correctly? That's probably the most important thing for the point of view of the assignment. And are the to-do statements filled in? There's not a lot of stuff in there about what should happen in some bizarre condition about error handling, so that isn't really part of it, unless you find a to-do statement that explicitly talks about that. Naturally, if you write production code, you'd want to be more careful with those kinds of things, but that's not really the point of this assignment. This assignment is to give people a chance to learn about how to use the Android Hammer framework more thoroughly. All right, last thing I'm going to do with this assignment is go ahead and kind of walk through the main activity a little bit. People had some questions about it, so I figured I would go ahead and cover that as well. So here's main activity, which extends activity. It defines various text views and scroll views and so on that are used to display the output. It's got a button that's used to play the game. Keep track of the program state, which is also an enum with run and reset. And we set the state initially to run. It's got an output strategy. It doesn't really matter what the iteration count is, of course. It's just basically something that you could use for testing to see whether scrolling is working. It's got an instance of the play ping pong object, which we use to start the ping pong game running. And then it has this other interesting thing called the delayed output thread. And delayed output thread is kind of an interesting little design that I'll talk about when we get down there. Here's the onCreate method. It does what they usually do. It calls up to the superclass, sets the content view, caches the various widgets that are needed for displaying various kinds of information, and it creates a new output strategy. I've also, in my implementation, added a few more things just to clean everything up more pristinely. I added an onDestroy method, which shuts down the threads and destroys the superclass. Here's what shutdown threads does. It goes ahead and quits and interrupts the delayed output thread and calls shutdown threads on the play ping pong thread. I added this a little later just because I thought it was a better way to clean things up. This was not part of the original solution, but it doesn't matter because you're not really providing anything here anyway. Here's what happens when you press the play button. If that button is clicked, then if we're in the wrong state, we reset. Otherwise, we figure out what state we're in. Are we in the run state? Are we in the reset state? Here's the run state. We go ahead and create a new play ping pong object, passing in the number of iterations and the output strategy. We then create a new delayed output thread, and we pass in the play ping pong thread to that as a runnable. I'll talk about that more in a second. Then we go ahead and we start the thread. So that thread is now going to be running in the background. And then we go ahead and we reset the view, so it now will say reset, which we can use to stop the ping pong operations from running. If somebody clicks reset at any point in time, that will shut down the threads from the previous run and then reset everything and then go transition back to the run state. Now, if we wanted to, we could be even more cool if we wanted to by using the state pattern. I probably should have done that just to show how you can use it, but I was just having a simple driver program, so I didn't get carried away. Here is the delayed output thread. The reason for the delayed output thread is to be able to block for up to a half a second before printing ping and pong, especially flashing ping or pong. So it's actually visibly noticeable or discernible by the user. And if you didn't do that, it would blink so fast you wouldn't even see what was going on. So we wanted to be able to do that, but we didn't want to block the UI thread. And as a general rule of thumb, it's not a good idea to do a sleep or a blocking operation in the user interface thread. And so we wanted to keep the program responsive by not actually having the user interface thread wait, but instead we have something called a delayed output thread. I also, another reason why I did this is I wanted to show people how to use a handler thread. And this was because they had to use a handler thread for the play ping pong implementation. So I wanted to have one concrete example that showed how it worked that you could look at to get some knowledge of how to set it up properly. So basically, as you can see, delayed output thread is going to extend a handler thread, and then it's going to go ahead and define a handler, which we call the delayed output handler. When we make this volatile, just to make sure it's visible properly, it's probably actually okay. I probably could just make it be, let's see, well, I don't think I can make it. Yeah, I can't make it be final because it's not initialized in the constructor. So it probably needs to be volatile so it's visible properly where it's needed. And then I also have this thing I call the completion hook, and I'll talk about that in a second. That's a runnable. And you can see the constructor for delayed output thread simply uses the completion hook to stash away in a local field, which is this field. And I'll explain why we need that in a second. You'll see later we call start on this thread. So in fact, actually, it's called up here. See right there, we call start on this thing. So that's going to start the thread. And then the on-loop or prepared method is going to be called. So when on-loop or prepared is called, we then go and create a new handler, which is the delayed output handler. And this, of course, is created in the context of the delayed output thread. It's a handler thread. So it's actually going to be associated with the background thread that's running. And at this point, only once delayed output handler is initialized do we go ahead and actually create the next thread in this pipeline of threads we're trying to create. So we're going to go ahead and create a new thread and start it, and we're going to give it the completion hook to run. And it's instructive to ask yourself the question, why do we do this? And the short answer is because we're trying to prevent race conditions from occurring where the play ping pong threads start and begin to call print before the delayed output handler is properly initialized. Now, we could do a cyclic barrier or some other synchronizer here, but that would just start to get complicated. So instead, what we did is we just kind of daisy chained this together, and we pass a runnable into the constructor of the delayed output thread. And when that guy is all initialized, he goes ahead and kicks off the next thread. So this is a simple, nice little pattern of being able to handle dependencies between startup of multiple threads of control. There are other ways to do this. This is the way I thought was cleanest without having to introduce a lot more synchronization mechanisms that we didn't talk about. Here's a method called run on delayed output thread. This is very much like run on UI thread, except this is going to run in the delayed output handler. And as you'll see in a second, we're going to see how this is actually going to be used. Here's the print method. The print method, of course, is the same print method that's called here in the output strategy class, or by the output strategy class. So output strategy takes a string, and it goes and it gets the main activities reference, and then it calls print. So that call here is this call here. This goes ahead and creates a new runnable, which we're going to look at here. And that runnable gets posted to the handlers thread using the run on delayed output thread call. So run on delayed output thread is just basically forwarding to the post method. So this will then get dispatched by this handler that's associated with the background thread. So this, whatever we pass into run on delayed output thread, the runnable that gets passed in there is going to run in a background thread. And when its run method gets called in the background thread, it turns around and it creates another new runnable, and it sticks this runnable on the UI thread. And this runnable's run method, as you can see, goes ahead and updates the display, printing the ping or pong text, and then going ahead and kind of flashing either ping or pong as the background screen in black and white. And then, and here's the reason why we have a background thread, we go ahead and we sleep for half a second before we handle the next message. So this allows us to be able to properly give some extra delay between flashing the results without blocking the user interface thread, because the blocking gets done on the delayed output thread. And you'll notice that if things get shut down, it's very responsive, because if sleep gets interrupted by the interrupt call, which occurs way, way, way back up here, if we interrupt this thread here, then sleep will wake up and go ahead and quit the looper and shut down. So that's basically the main activity.java file. Now, once again, of course, there are other ways to do this. There are probably even better ways to do this. That's just the way that we did it when we made the assignment, and I'm giving you the explanation for why we did it that way. Okay. So someone asked a question about hard coding the solution to be a particular constant for the iterations count rather than using the max iterations count. I mean, as long as the program worked, that's probably okay. I would put a comment urging them not to use magic numbers in their code. It's a very bad idea to use magic numbers in your code, but it's not really wrong from the point of view of what the rubric was asking about. There's a question about deciding when to use the Hammer framework or the async task framework. That was covered in last week's lecture that's about comparing and evaluating the different Android concurrency frameworks. So please go back and watch that video. I don't like to repeat stuff that were already covered in videos because it was already covered in much more detail. So there's an extremely detailed analysis of Hammer framework and async task framework across 5 or 6 different dimensions. So please go back and watch that video. Let's see. There was a section about performance tips. Oh, this is interesting. So Iago points out that they took out the section about not using enums from the documentation because it turned out there was no problem. So that's good to know. I didn't think that there really would be. It doesn't seem to make a whole lot of sense. All right. Let's see. Oscar has a question about using the view, but I don't see the question. Oh, here we go. When I run with 10 iterations, the view doesn't scroll. Oscar, you need to update to the later shells. That fixes all those problems quite nicely. So that's one reason why I had updated those things. The first version didn't scroll properly, but now it scrolls quite nicely. And I think if you watch the video, it shows that. So it's another person talking about enums. Doesn't sound like there's actually a problem with enums. That confirms my expectations. Let's see. Coursera fails to allow resubmissions before the deadline. So usually what happens is right before the deadline, everybody's pounding away at the server, and so it gets slow, but you should be able to resubmit if you're patient. A better way to do it is not wait to the last couple of hours to try to submit, because you've got lots of people, thousands of people submitting at that point, which of course is going to bog down the server. There's also a grace period, I think, for up to an hour after the deadline. But once that deadline passes, we cannot reopen it. So you need to make sure you get stuff done ahead of time. If it's not outputting done, what score to give? Well, if it's not outputting done, it probably has a concurrency bug. It probably is leaving a thread that is not finishing, so it's not joining properly. So that's probably not really producing the correct output. So that is actually covered in the rubric. Okay, so that looks like all the questions we had on the programming assignment number 2. Keep in mind that programming assignment number 3 is going to be due basically a week from yesterday, I think it is. And you can make programming assignment 3 as simple or as complicated as you want, as long as you implement the requirements. And so take a look at the index.html file to see what the requirements are. The main requirements for assignment number 3 are that you have to use a pair of async tasks, number 1, and you also have to be able to properly handle screen rotation without having your program crash or give the wrong results. And other than that, though, you're pretty flexible as far as what you can do. I gave you a couple of functions. You're welcome to change those in any way you see fit, because you're not actually going to be you're going to be able to provide your own solutions. So you'll provide the entire solution, so you can modify those if you don't like what I gave you. Let's see. So there's a question asking about getting a runtime exception because they're sending a message to a handler in a dead thread. Well, if you take a look, go back and take a look at my solution, and you'll see that I check for those situations to make sure that I'm not trying to send messages to a thread that's dead. And you may need to write some defensive logic into your code to handle that properly. Okay, what I'd like to do now is I would like to go ahead and finish up the remaining lecture material, and then we will be all done with all the lectures for this part of the MOOC, which is kind of exciting. All right, so where we left off last class. Oh, and sorry, one more thing. Somebody wants to know, where is the screencast for assignment number 3? Well, if you take a look at the lecture material for week number 4, you will see that it has an assignments section, and my screencast is in the assignment section. It's probably the most latest thing that was uploaded. So just take a look at the lectures website under week number 4. Okay, where we left off last time, we had just finished up talking about the intent, applicability, structure, dynamics, and so on of the active object pattern. And now what we're going to do is we're going to talk about the implementation of the active object pattern. And we're going to talk about how it's implemented and applied in Android, of course, because that's what we're focusing on. So if you implement the pattern, the first thing you need to do is implement the invocation infrastructure. This is the stuff that will actually send messages back and forth. So one thing you would do is you'd implement the proxy. You'd basically create a concrete method for each method invocation that a client can make. Here are some examples of methods that you could call. The proxy pattern is described at this link. There's also going to be more coverage of the proxy pattern in the communications MOOC that's coming up starting in a couple weeks. And of course, you can find the source code for all this stuff in the Android release. You then want to go ahead and implement the method requests. And method requests can either be method calls that are transformed into messages by the proxy, or they can just be messages themselves. The Android method requests and proxies are simpler than the full-blown pattern described in the POSA 2 book. But the Android way of doing this is a variant. It's the so-called message passing variant that's described in the POSA 2 book. The next thing you need to be able to do is you need to be able to implement the activation list. So we have a message queue, And this is what's used to insert and remove a method request. In this case, of course, we're using messages, but same basic idea, that a message would be what a proxy would generate anyway if we had a more full-blown proxy. And we're basically going to implement the message queue as a synchronized buffer shared between a client thread and the thread or threads where the scheduler and the servant, which are other roles in the pattern, are going to run. You can look here to find the source code for the Java source code for the message queue. There's also C code and C++ code that's used for some of the low-level parts, but you don't have to know how that works in order to use it effectively. Next thing to do is to implement the scheduler. The scheduler manages the activation list, and it executes the method requests in the appropriate order. And in this particular case, it executes them in the order that they show up when the next method is called, which you can see in the looper.java program. And next just blocks waiting for the next thing to happen. And the next thing to happen could either be a message showing up because somebody passed it via send message or by a post, or it could also be showing up because the time period elapsed. And that's all handled under the hood, deep in the bowels of all this stuff. The next thing to do is implement the servant. The servant is what actually is going to handle the request. In the case of Android, this is the message handler. And it has a handle message method that takes the message that was passed by send message, and then it goes ahead and switches on that and does various things. In this particular case, it's going to set some visibility parameters and progress bar updates and so on and so forth. And then the other thing you need to do, if you have two-way communication between a client and a server thread that are communicating via the active object pattern, is to determine the rendezvous and return value policy. So how do you get the result back, if any, from the servant back to the original caller? And the way you typically do this in Android, of course, is you would pass a reply handler with the message. And so you can see here, for example, that we get a reply handler that comes in as the OBJ field, the obj field, and the message. We then go ahead and make another message, and we make the reply handler be part of that, as you can see here. And then we go ahead and we send this back to whoever sent us the message. So that'll go back to the thread where the message came from. This is a very common idiom. You can actually see when we covered the material on assignment number 2 that we used an idiom almost exactly like this in order to be able to get a message that had the reply as the OBJ field, and that then got sent back to the target. All right, so that's basically some implementation details. Looking at Android as an example of this. Android's by the way not the best example of the active object pattern, but I wanted to keep the example focused on Android. I'm going to show you another example of applying active objects in Android. This is a little bit more interesting example, and this is something that we'll talk about in the next MOOC called the async query handler. An async query handler is basically an Android helper class that is used to invoke calls to a content resolver asynchronously with respect to the user interface thread. So in other words, we can query a content resolver to find out about persistent data values without actually blocking the caller. So let's first talk about what is a content resolver. A content resolver is basically a proxy to access a content provider, which is typically a facade for accessing an SQLite database table or tables. And again, we'll cover more about content resolvers and content providers and content and databases like SQLite in the next MOOC, but this is just to give you sort of an overview. So here you see an example of what happens if you don't use the async query handler, if you just make a synchronous call. So if you call query on a content resolver, if an activity calls query, that will go ahead and block. And so in this particular case, it would query the content provider and return the result, but that will block synchronously. And we all know that blocking things that can delay or wait or sleep or whatever for a long period of time is a bad idea, because the UI thread will give you the application not responding dialog, and you'll probably have your program shut down. So an alternative way to do this is to use the async query handler. And this is where the active object comes in. And of course, the reason this pattern is called the active object pattern is because the methods that are being called are active instead of passive. So a passive method borrows the thread of control of the caller. The monitor object pattern works that way. Whereas an active object, in an active object pattern implementation, a method runs in a separate thread. So the thread that invokes a method is not the same as the thread that executes it. That's what makes it active. And this is all based on something called the actor model, where you have active objects that are actors, that are given their own volition or their own free will to run independently of the threads that call them. So returning to this example, you can look at async query handler if you want to see how it works. You would, instead of calling a blocking query, you would invoke the start query method. And that method will pass the query off to the query handler and then return right away. So it doesn't actually block. And then the handler goes ahead and runs in the background. And what that does under the hood is it uses the Android Hammer framework to send a message from the my async query handler, which is basically from the async query handler, which is basically the proxy in the pattern. And that creates a message that contains the query, and that's passed to a worker thread, which is playing the role of the scheduler. And of course, it's a worker thread has an activation list, which is the message queue. And that handle message method that gets called in the worker thread pulls off the request that's encapsulated in the message, pulls out the query, and then it runs it in the background and gets the results. And that can block because it's running in a background thread. And when it's all done, it returns the result back to the original activity, and it does a send to target, and that ends up dispatching a callback called on query complete. And this will end up basically having the result passed back to the activity in the user interface thread. So it's kind of cool. This is really a really good example of the active object pattern in Android, because we have proxies, we have method requests, we have schedulers, we have activation lists, we have basically futures, we have callbacks to the futures, et cetera, et cetera. So this is much more of a complete implementation of the active object pattern. But the cool part is that it encapsulates the active object implementation we saw in the Hammer framework as a portion of that. So it just shows a more powerful example. And you can see here internally, it uses the active object pattern to do the various sending. You can look at the code if you're curious. I'm not going to walk through it all in great detail, but you can look at the code here and see what it does. It's pretty cool. Once you understand the Hammer framework, understanding async query handler is pretty straightforward. So to summarize, Android handlers and messages implement a subset of active object that enables communication between a client and a handler where they run in separate threads. You can extend the basic Hammer framework facility to add support for better proxies and servants and futures like async query handler does to make more complete active object implementations. You can take a look here for yet even more information about active objects in Java. And of course, it's important to remember that the Java Executor Service Framework also implements the active object pattern. That's a very common way to use active objects in Java, where you can submit callables that run in a thread in a pool of threads. So that's yet another example of the pattern. And you can find out more about the Executor Service here. Okay. So that's the end of the slides. Let's pop back here and see if anybody has any questions. Someone wants to know about the video lecture by SureLogic. So we're going to be posting a detailed walkthrough by Tim Holleran from SureLogic here shortly, probably in a day or so, which walks through assignment number 1 and shows how to apply the SureLogic tools to find a variety of deficiencies, both in the skeletons and in various implementations. And we're waiting for them to release their next release of SureLogic because they found a bug in SureLogic that they had to fix, and so his video uses the version that they're releasing here. So that's why we haven't put that video out yet. So it'll come out soon. All right. Oh, good question about assignment 3. What are the options for handling activity and fragment shutdown if the back button is pressed while the thread is still running? So there's a variety of things you can do here. So my implementation, which I walked through, which I think you can find in maybe week number 3, I did a walkthrough of my implementation very quickly, just to give you a sense of how you could structure it. You're under no obligations whatsoever to structure it that way, of course. I actually have a model very much like assignment number 1, where I have a main activity, and that main activity spawns a couple of activities: a download image activity to download the activity, download the image, and a filter image activity for filtering the downloaded image. And those activities then use async tasks to do their work in the background. And they also have a cool little framework that uses retained fragments and so on. And so if during the time when you're running, you press the back button and so on, then you can simply cancel the thread. That's if you're doing a back, you probably want to cancel the thread. That's the smartest thing to do in that case. If you're simply rotating the screen, then you probably don't want to cancel the thread because there's no need to. But if you're going to go back and the activity gets destroyed, then you probably actually want to cancel the thread. And so the way you would do that, of course, if you're using async task, is by using the cancel method on an async task to go ahead and shut it down. All right. Question about the active object pattern. The activation list dispatches the service request to the servant and waits until the servant call terminates and then dispatches the next service request. Isn't this slowing down the dispatching runtime? So let's talk about that, right? So first of all, there's lots and lots and lots of different ways to implement these patterns, and the typical pattern write-up will talk about some of the variations. Sometimes, if the pattern doesn't describe the variation that you're interested in, it's trivial to figure out how to solve that. So let's work through what you're saying. So first of all, you're saying that when the scheduler thread pulls off a request, a method request from the activation list, when it pulls it off and it goes ahead and calls back the callback method on the servant, does it block until the servant's method finishes? The answer is typically yes. And the question becomes, is this a problem? And the answer is no. And the reason it's not a problem is the following. If that's going to take a long time and you want to be able to make the active object responsive to other things that are happening while that call is blocked, the easiest way to do that is simply to have a pool of threads running inside the active object. So the scheduler will actually be managing a pool of threads. That is exactly the way that the Java executor service works. So the Java executor service has a pool of threads, and when a call method is dispatched on a callable, while that thread is blocked, all other threads that are in the pool can run. And of course, if you know anything about the Java executor service, you can control the kind of thread pool that's used, and so you can manage the number of threads that are used there. So one answer is just use a pool of threads, no problem at all. Another answer is, if this is an issue, then don't have your servant method block, but instead have that method do something that will allow the dispatch scheduler thread to go back and return right away. So the easiest thing to do there is either to take the request that comes in and queue it for later processing, or spawn another thread, or do whatever you need to do in order to avoid that from blocking. So those are the typical ways you would combine the active object pattern with other patterns in order to avoid situations where a single thread that's running in the scheduler blocks for a long duration of time. That's a good question, but it's not really an issue. Let's see. So the question about the quizzes, the due date for the quizzes is, for all the quizzes, every single quiz should be 11:59 p.m. Central Time April 29th. And of course, depending on what time zone you're in, that may be a different time. It may be appearing as April 30th to you. Please go read the frequently asked questions file, and it explains how quiz deadlines work. All quizzes are due the last day of class at the end of the class, which is at 11:59 Central Time USA. So that's why they're all displaying the same. Everything is there. There's only a hard deadline. There is nothing else but a hard deadline. Everything is due the very last day, and that gives people maximal flexibility to do the quizzes at any time. You can start the quizzes an hour before the hard deadline, and you should be perfectly fine, assuming you can get them right within that time. Okay, let us now go on, and we will talk about another pattern. This is the final pattern in our group of patterns we've covered here. We've covered, just to enumerate things, we've covered the thread-specific storage pattern, we covered the command processor pattern, we covered the active object pattern, and now we're about to cover the half-sync, half-async pattern. If you're curious, there's also the monitor object pattern, which I put another recording up on. I decided ultimately not to cover that because I haven't completely converted it over to a version of Android that I like, but it'll at least give you something to look at if you're curious about it. Okay, the pattern we're about to talk about now is the half-sync, half-async pattern, and we're going to see how this pattern works, and then later we'll talk about how it's used in how it's implemented and applied in Android in a detailed way. Here's the context of this. We often have applications in concurrent systems that need to perform both synchronous and asynchronous processing of services that have to communicate with each other. And the threaded downloads application is a good example of this particular context, which you can look at the code here. We've gone over it in week number 2 and week number 3, but you can go look at it if you want. The problem here is that we don't want the simplicity of synchronous processing or services that want to be simple shouldn't need to have to handle the complexities of asynchrony. Asynchronous processing can be a little tricky because you have to not block and you have to restrict the kinds of things you can do. Synchronous processing, on the other hand, is much simpler, but not everything can work in a totally synchronous way for a variety of reasons. So for example, here's a little snippet of code from the download application class, and this basically is used to get a file at a particular URL. So it downloads the contents of an image at a particular URL and converts the contents into a bitmap, which of course is an Android representation of an image. And we need to have the downloading run in a separate thread because we can't do it in the main thread because it would take too long, and you're not supposed to call networking calls from the main thread of control. Likewise, we don't want to make everything be multi-threaded, if for no other reason in Android that it can't be entirely multi-threaded, because user interface operations have got to run in a sequential way in the main thread of control, or the user interface thread. So there are these different issues we're trying to deal with. We're trying to deal with simplicity and complexity, and synchronous and asynchronous, and all the different combinations thereof. Another thing is we don't want to have to spawn a lot of background threads. We don't necessarily want to have a thread per request model. That could be prohibitively expensive as well. So what we're going to do is we're going to decompose the system into 2 layers, a synchronous layer and an asynchronous layer. And as you'll see, the synchronous layer is going to have a bounded number of threads that are typically some function of the number of cores or CPUs in order to scale up performance via concurrency without creating an unbounded number of threads, which would become prohibitively expensive. And then we're going to add a queuing layer. And the queuing layer basically is used to mediate communication between the synchronous layer that we just talked about that's got threads and the asynchronous layer. And the asynchronous layer, of course, is going to be used to actually do the processing that can only run in one thread of control at a time. So let's go ahead and talk about this design in terms of patterns. So this way of organizing things is called the half-sync, half-async pattern. And it's used to decouple asynchronous or async and synchronous or sync service processing and concurrent services systems by introducing two layers that talk to each other. One for the synchronous processing that can't block, one for the synchronous processing that can block. And we do this to simplify programming without creating an extraordinarily large number of threads for things that really shouldn't be multi-threaded. And here's kind of how the pattern looks. You can take a look here. This is a POSA 2 pattern. And this illustrates how the pattern works. You could also read the POSA 2 book and get more information. You should apply this pattern when you want to make things scalable and efficient, and yet also make them simple to program. Of course, simple is a function of understanding the pattern. And you also should use this pattern when there are constraints on certain types of operations in certain contexts. Long duration versus short-term operations, blocking versus non-blocking operations. And as you all know by now, hopefully, in Android, the short duration and non-blocking operations can run in the asynchronous layer or the user interface thread, and the long duration blocking operations need to run in the synchronous service layer. And then there's a queue of various sorts that communicate, typically a message queue. This pattern is very, very widely used in modern GUI frameworks. It's very, very widely used in operating system kernels. You find it all over the place. Here's how the pattern is structured. So you have the asynchronous services layer, which would be in Android, the user interface thread. There's only one of these, and nothing can block, so it's an asynchronous processing context. We have a queuing layer, which is typically a linked blocking queue or a message queue or some other kind of queue that the Hammer framework or the async task framework provides internally. And then we have the synchronous services layer. And this is where the background threads run. And they're typically a fixed number of them. And these threads can afford to block because they're not interfering with the user interface thread. Here's the dynamics of the pattern. The event handling runs either reactively or asynchronously. It's typically sitting there waiting for something to happen, such as blocked in the next message on the message queue for an Android activity. And then when work comes in from someplace like touchscreen event or some other thread, that will basically end up being queued on a background queue, which in the Hammer frame would be the message queue. In the async task framework would be the queue that's used by the executor framework of Java. And then one of the threads that's running in those pool of threads or a thread will wake up, pull the request off, and then go ahead and process it. And that processing, of course, can take place synchronously. So basically, this allows the synchronous services to run concurrently, both relative to each other and also relative to the asynchronous service or services. So this allows multiple things to go on while still allowing a single thread to do the user interface and user-facing operation work. There's good and bad things about this pattern. Some of the good things is it simplifies the programming while still allowing things to run concurrently. Not everything is concurrent, just the stuff that's synchronous is concurrent, and the stuff that's not synchronous, like the user interface toolkit operations, those are done in a non-blocking or a short blocking, short duration manner. So we don't make everything be threaded. We also separate concerns cleanly. So the synchronization mechanisms used or policies used in the async part can be different, typically much easier than the synchronization policies used in the synchronous part, where they actually have to have pools of threads and locks and so on. And we also make it easy to know how to talk back and forth because the queuing layer mediates communication between the two different realms, the sync and the async layer. There are also some downsides. Whenever you start moving between threads, there's an overhead. This is true in any language. It's true in multi-core systems. It's getting faster over time, of course, because processors get faster and so on. But there's an awful lot of caching that takes place. And so moving things between threads takes some time. So typically you don't want to you want to make sure that what you're doing runs for a while so the overhead of the boundary crossing penalty will be minimized. And so some things you get there are context switching, synchronization, data copying, overhead, and so on. Another downside is that there are some benefits from asynchronous I/O once you understand the asynchronous model. In particular, you don't have to think very hard about synchronization because it's all handled via the asynchronous processing. And so this particular pattern doesn't really give the synchronous services access to asynchronous operations. There are other patterns that can be used for that. And of course, it's always the case with any concurrency usage that the debugging and testing is harder because you have to keep track of everything, and it's tough. Let's talk about some known uses. So the Unix networking subsystem, if you take a look at the Unix operating system, it uses the half-sync, half-async pattern to separate out the kernel level processing from the application level processing. And the example that's used in the half-sync, half-async pattern write-up explains this in great detail. Object request brokers often use this pattern as well. If you take a look at this paper, it talks about some object request broker implementations that we implemented years ago that use this pattern successfully. The Android async task framework, probably my favorite example. We looked through the code of the async task framework in detail last week, week number 3. And if you go back, now that you know the pattern and you look carefully at it, you'll see how the pattern is shown in the code, and we'll look at this in a second. And to summarize this part, you can separate concerns between synchronous layer and the async layer using a queuing layer, which makes things easier to understand, debug, and evolve. You don't degrade performance unduly, and you keep things nicely put in the right places. Another nice thing about using this pattern is because it uses a queuing layer, you can reprioritize the order in which messages are processed. Now, Android doesn't give you a lot of mechanisms for doing this. The only thing you can do in Android really is use timeouts to indicate priority. But that's kind of a crazy way to do things. So you really can't use priorities in Android. But there's lots of other implementations of this pattern where you can prioritize the way in which stuff shows up. Okay, we have a couple of questions, and then we're going to talk about the implementation of the half-sync, half-async pattern and its application in Android. One question is, how does active object relate to command processor? So first of all, I think the question you're really asking is that the question is phrased is active object equal to command? So that's not really the right comparison. Command pattern really has nothing to do with concurrency at all. Command pattern basically just says encapsulate some functionality in an object and then be able to pass that object around and store it and redo it and undo it and so on. So it's not really related to concurrency in the least. Command processor, which is a POSA 1 pattern, is actually related to concurrency. And we talk at length about this in week number 3, but I'll give you the quick summary right now. So as you can see, if you take a look at the Android Hammer framework, there are ways of posting runnables, and there are ways of being able to send and handle messages. And so if you go back and you watch the videos from week number 2 about an overview of the Hammer framework, it talks about these two approaches. In fact, that's pretty much the whole discussion in week number 2 is comparing, contrasting posting and processing runnables versus sending and handling messages. And if you go back and watch those videos, you will then understand the distinction between command processor, which is like posting and processing runnables, and active object, which is like sending and handling messages. And so I'll kind of leave it there for now, but those are the places to go to find out more information about that. I also gave that answer last week when we were talking about the command processor pattern and the active object pattern in the first half of it. So there's lots of stuff in there. But no, they are not the same pattern. They have very different outcomes, just like posting runnables and sending messages have very different outcomes as well. Can I please give an example of the active object pattern that I have for the command processor? Oh, as a call center. So what's a human known use of active objects? Actually, just about anything that you would do in real life, you are typically acting as an active object. So people give you work to do, and you need to do the work and then you pass the message on either back to them or you give the message on to somebody else. And so a person is kind of an active object because people are giving you work to do. Imagine, let's come up with a good example. Here's a good example of active object in real life. This is one of my favorite examples, by the way. So in the United States, everybody tends to go to fast food restaurants. It's one of the things we've unfortunately exported to the rest of the world is an obsession with eating fast food. And a fast food restaurant is a wonderful, wonderful example of the active object pattern. It may not be a wonderful way to dine and to keep yourself healthy, but it's a great example of the pattern. So what you do in a fast food restaurant, like this may or may not make sense to you, but if you're an American, there's a place called Wendy's. And in Wendy's, when you go to Wendy's and you order a hamburger, they cook your hamburger for you, especially. The hamburgers are not stored in a heat lamp and just pulled out and given back to you. So when you go up to the counter at Wendy's and you order a hamburger, they will cook it for you in real time. So one of the consequences of that is you, the restaurant owner, the Wendy's restaurant owner, don't want to block at the cash register with a person who ordered a hamburger until the hamburger is finished cooking, because that would be very, very slow throughput, because each person would have to wait for the hamburger to finish cooking. Moreover, the cook, who plays the role of the scheduler, by the way, in the active object pattern, can actually cook multiple hamburgers simultaneously. So there's no reason for you to wait synchronously for the hamburger to complete. So when you place your order at Wendy's, they give you a little plastic tab which has a number on it, like the number 42. And that plastic tab is a future. And that future is used by you, the person who's the client ordering a hamburger, to get the hamburger that's your hamburger later on when it's finished. So you submit your order. The person who takes your order is basically playing the role of the active object proxy, and they are converting the words you speak to them into some kind of request that gets put in a queue that the cook, who is the scheduler, will pick out and then go ahead and start cooking your hamburger. So the thing that's used to keep track of the orders is the activation list. The person taking your order is the proxy. Notice that the proxy also gives you back a future, which is the little plastic tab. And the cook, who is the scheduler, pulls the orders off, cooks the hamburgers, and when the hamburgers are done, they are then delivered via the future. And there's two ways for the future to be delivered. You either go back periodically to the pickup window or the pickup counter and you poll and say, is my hamburger ready yet? I've got number 42. And if it is ready, then you pick it up, or you wait there at the pickup window, or you go back and check your iPhone or fill up your drink or read the newspaper or whatever you do. Or another model is when your order is ready, the clerk or somebody, the runner, can take your hamburger and come deliver it to you at your table. That's the callback model. So that's a very nice example that illustrates how all the roles in an active object can be applied in everyday life, eating terrible, junky fast food. Okay. Just a comment on the naming of the half-sync, half-async layer. UI thread is in the async layer, yes, and the background threads are the sync layer. Yes, that's correct. So what that means is that the background threads can block synchronously, which is why they are part of the synchronous layer. And the things that are running in the UI thread cannot block. They can only run asynchronously or reactively. And so they are part of the async layer. And if you read the pattern description, you'll see a little bit more discussion about the naming conventions and so on. Okay, we are getting close to the end of all this. Let me bring up another slide set. All right, this is the second half of the half-sync, half-async pattern. So in the second half of the half-sync, half-async pattern, we're going to talk about how to implement this pattern and how it's applied in Android. So the first thing you do, of course, is you decompose the overall system into 3 layers: synchronous, asynchronous, and queuing. So in Android, of course, we would define the appropriate roles and appropriate methods and so on. Things that are short duration services will be done in the async layer because they can't block. They have to be executed asynchronously. So for example, things like on pre-execute, on post-execute, and so on, those are the short duration stuff, and they're going to be executed in the UI thread. And then the stuff that's the long duration services are going to be implemented in the synchronous layer in a background thread, and they can block synchronously, which is why they're in the synchronous layer, which is why this pattern is the half sync, half async layer. We then define a queue that's used to interact between the different layers. And as you can see here in the Android implementation, there's something called the thread pool executor, and it has a blocking queue that's used to hold the various tasks and hand them off to the worker thread. So this is basically the way we mediate access between the sync and the async layers. We then go ahead and implement the services in the synchronous layer. So here's an example from the download async task example that we have in the POSA 14 examples directory. So you can see it's going to download something in the background thread. We implement the services in the asynchronous layer. We do the on pre-execute and on post-execute. Those are performed in the user interface thread. They don't block for any length of time. They just do things like display the bitmap and dismiss the dialog. We then have a way to be able to implement or reuse the queuing layer. And this, of course, uses the underlying blocking queue mechanisms that Java provides with its blocking queues, like linked blocking queue or array blocking queue, and so on and so forth, or the synchronous queue, synchronized queue. So these are blocking calls. Take is a blocking call, and so on and so forth. And here's how this thing actually gets applied in Android. So this is looking in more detail. Assuming we're running the async task with a thread pool executor, then we're going to have the user interface thread call execute to do something like download a URL, and that will then execute that request in a thread, in a pool of threads, and then the results will be passed back, and that passed back via this queue. Actually, it's a set of queues. One queue goes to the pool of threads. There's another queue to get back to the UI thread, and those are used to mediate access between the different layers. And if for some reason something in the synchronous layer takes a while because the network is slow, or there's a large image to download, or the server is busy, that's okay, because it doesn't block other tasks that are running in other background threads. Okay, to sort of wrap all this stuff up, Android's async task implements the half sync, half async pattern, and it allows us to be able to encapsulate creating background threads that run independently from the user interface thread. You could also use it to report the progress of running tasks. The async task framework is a very sophisticated implementation of the half sync, half async pattern, and yet it's all right there. It's all directly applicable. If you read the pattern and you look at the various roles, they all appear in the half sync, the async task framework. And what makes it more sophisticated is that there's multiple interactions, because you're passing requests from the UI thread to the background thread. Then you can pass progress results from the background thread to the UI thread periodically during the background processing. And then when you're all done, you pass the result of the do in background method back to the UI thread as well. So there's lots of different ways to interact. Okay. So that is basically the end of all the lecture material for the course. Of course, we will have lots more stuff when we do the POSA MOOC, the POSA Communications MOOC, or Communication MOOC, that'll start here on May 6th. And in that MOOC, I'll give you a little overview of what's going to be covered in that MOOC. If anybody has any questions, by the way, feel free to ask them now, because we're going to wrap up here shortly. So in the next MOOC in the specialization, we're going to do the following. We're going to start off by covering Android services. And as you'll discover, Android services are basically functionality that can run in the background without interfering or being interfered with by the application activities or fragments that are running. And so they're used for doing sort of long duration operations. And one nice thing about a service is that they are not affected if you rotate the phone. So all that crazy stuff we've been doing with rotation would not be done in quite the same way with a service, because you'd be able to manage things more effectively. So basically, the service runs in the background, and as we'll see very quickly, there's two kinds of services. They're bound services and they're started services, and we're going to talk about a whole bunch of different ways to communicate with bound and started services, ranging from passing them intents, to using messengers to pass messages back and forth, to using the Android Interface Definition Language, or AIDL mechanisms, to pass data back and forth that way as well. So we'll talk a lot about different ways of doing services, and that'll probably take, I would guess, the first 2 weeks of the course to cover all the services stuff. After that, we're then going to have a week of material on HTTP programming, so using the HTTP programming model and client-side support in Android to communicate with servers that run in a cloud or a web server somewhere. And so we'll talk about that, and we'll also talk about some pretty cool mechanisms called retrofit that give you the ability to encapsulate some of the low-level details of HTTP programming and the use of JSON behind nice proxies. And this will introduce some more patterns like the proxy pattern that we'll talk about. And then in the fourth and final week of lectures, we'll cover some patterns. So we have a lot of patterns we could cover. We'll probably cover a subset of them. We can talk about the activator pattern, which is used with services. We can talk about the proxy and broker patterns, which are used for services as well. We can talk about, which is used for the binder mechanisms that are part of Android for communication. We could talk about publish, subscribe. There's a whole bunch of different things we can cover there. So that'll round out basically the next MOOC. The following MOOC will then start moving more into cloud programming, and we'll talk more about accessing data in the cloud. And in addition to talking about various cloud programming abstractions like Spring and ways of accessing Spring programs from Android phones or just from web applications in general, we'll also spend a little time talking about Android content providers, which are yet another way of accessing persistent data. So although we'll be talking a lot about the cloud services, we'll also be spending a little bit of time talking about some of the Android services for accessing data. If for no other reason that the reason we put those things together is because oftentimes you use content providers as caches to cache data that's either downloaded from the cloud or will be uploaded to the cloud. So we'll talk about synchronizing content providers with Android on the Android device with cloud databases using various things like sync adapters and so on and so forth. So that's giving you a little bit of an overview of what's going to come up over the next few months. And then after all that stuff, of course, we'll have a nice capstone project for those of you who completed the other courses. Is there a book of patterns used specifically for Android, similar to the Gang of Four or POSA books? So Android implements a lot of patterns, and it implements a lot of Gang of Four patterns. It implements many POSA patterns. So we're actually in the process of beginning to rewrite the POSA 2 book to use Java and Android as the examples, as opposed to the examples we have there now. I don't know when that book will be done, but that would be a good book to keep your eye out for later. Submissions to the assignment 3. Should we submit the complete project directory? Yes, please go read the steps for submitters, and it tells you to submit everything. You need to do that because the person who reviews your code is going to have to be able to make it work. They won't have anything else. How long did it take for me to master Android programming? Well, I wouldn't say I've mastered Android programming by any stretch of the imagination. I've got a pretty good handle now on the concurrency portions of Android and the communication portions of Android, but there's still lots and lots and lots more to mastering Android. And it's taken me a number of years to get to the point where I feel comfortable with all the concurrency and communication elements. Having said that, of course, because I knew the patterns, it didn't take that long to get up to speed pretty quickly with those capabilities, because they're more or less the POSA 2 and Gang of Four stuff, so it's pretty straightforward. That's why we have a specialization. That's why we have a 6 or 7 course sequence, depends how you look at it, because each of us brings something to bear where we are experts at, and doesn't require all of us to try to master everything. But as you can imagine, Android's a moving target, so it takes a while to come up to speed. The good part about learning the patterns is that when you move to a new environment, because let's face it, Android is really cool, but it won't be the final word in mobile device programming. So when you learn patterns, when you move to a different platform, all you're really doing is just mapping your knowledge of patterns to a new language or a new framework or a new architecture. But many, many, many of the overall approaches are pretty much identical. So it makes it easier to learn. The last capstone project, we had 3 different assignments that we came up with. One was a symptoms management application for doctors and patients who have throat and neck cancer, to try to help give information about their pain levels. We also had an application that was called Mootibo, which was a movie trivia game application. And the final application was something called Potlatch, which was basically a way of sharing photos and text with your friends, kind of a sort of like a combination of Twitter and Facebook. And so students could pick any one of those 3 projects that they liked, and then they had, I think when all was said and done, they had something like 7 or 8 weeks to complete the capstone. We're thinking about making it more like 8 weeks this time, because we learned that it took people longer than they thought to implement the projects. The other thing that we did differently this time than we did the first time is we're giving these mini projects in every one of the MOOCs, where you get a chance to actually write a complete application from scratch. We didn't do that before. Last time we did it, people only filled in the stubs, which meant that if they didn't ever do the assignments from scratch, when they got to the capstone, they struggled to figure out how to do the things from scratch. So by now, everybody should start to feel comfortable building an entire application from the ground up. And we've got a whole bunch of exciting new things that we're going to have this time as the projects, which I'll talk about as things get further along. When I put my assignment 2 on my tablet, it replaces assignment 1. I don't know what you mean by that, because they have different project names. So they're each called something different, so they shouldn't replace them. I have them all running at the same time, and there's no problem with that. Naturally, if you want to rename them, go for it. There's nothing that stops you from changing anything you'd like, just as long as you submit the programs that can be understood by the graders. Let's see. What's an example of the strategy pattern versus a template method pattern? So the main difference between them is that template method requires inheritance in order to override different steps in the algorithm, whereas with strategy, you don't need to use inheritance. You can use other forms of pluggability, such as functors in the C++ standard template library. And so if you take a look at a video on the asynchronous task framework, which was from week number 3, it gives examples of both the template method pattern and the strategy pattern in the same example, async tasks. So async task has the use of template method for its hook methods, things like on pre-execute, on post-execute, do in background. Those are all hook methods that are invoked when you call the execute template method. But if you want to change the executor that's used, you can plug in different executor strategies. And plugging in a different executor strategy to the async task does not require subclassing async task, whereas changing on pre-execute, on post-execute, or do in background does require you to extend or subclass async task. So that's kind of a difference about the use of subclassing and not. Can you tell us about assignment 4 and the mini project for this concurrent part? Well, assignment 3 is the mini project, because you're given almost no skeletons whatsoever, and you have to write the whole thing yourself. So you have to write the manifest file, you have to write the main program, you have to write the various async tasks. So that is the mini project. If you go take a look, you'll see that that's exactly what it's called. It's a mini project. Okay, so I think that is basically it. If there are any other questions, please feel free to ask them on the discussion forum. I will have a virtual office hours next week. It'll probably be on Thursday next week, because that way people will have a chance to submit assignment number 3, and then I can go over my solution, which of course may look absolutely nothing like your solution whatsoever, but that'll help us to start to kind of calibrate the peer grading portion of assignment number 3. So it's been lots of fun doing the live lectures. I think this has worked out reasonably well. It hasn't been perfect, but it's not too bad. And I look forward to hopefully seeing all of you again in the upcoming POSA communication MOOC. Thanks very much.